The process about which we have to talk today is friction, stir, spot, welding. And this process has been primarily developed for joining of thin sheets in automotive sector. So here you can say the metallurgical continuity between the two sheets is realized by the controlled deformation of the two sheets. So here what we do, since this is a one variant of the friction stir welding, so the two components to be joined, say mostly in lap joint configuration, this welding process is used. So just like the FSW tool, here also will be using one tool having the shoulder and then pin. Okay, so this pin will be gradually plunged through the top plate, okay, like this. And this plunging has to be very gradual because a lot of forces will be generated as the metal is at low temperature. So in order to avoid the breakage of the tool, it is important that the plunging is done very gradually. So this is shoulder and this is pin and this is rotating. You can say the rotating pin. Rotating tool is plunged gradually, and then it is allowed to penetrate into the other sheet as well. This extent of penetration in the other sheet is extremely limited, maybe 10%, 20% of it, the second sheet thickness. So once and when it is done, this is just like through thickness penetration through the top plate, followed by partial penetration into the bottom plate. And whenever this kind of the plunging is done, there will be continuous stirring and the deformation of the metal in vicinity of the pin, both from the top as well as the bottom plate. And because of this stirring and movement of the metal in all around zone in vicinity of the tool, the metallic continuity is established. But this continuity is very unique in terms of the geometrical features at the interface, and which in turn will be governing the joint load carrying capacity of the joint. So that typically in these joints you will see a typical hook of this kind is formed. This is the bottom plate, and here you will have the all stir zone here in the upper side, all stir zone. Similarly, some kind of the hook is formed other side as well. It is like this. So this is the bottom plate, okay, and this is the upper plate. So the geometry of these hooks, and here there is a nugget. You can say this is the nugget formation, which is the result of primarily the deformation and little intermixing. So primarily it is this nugget is made of the top plate, and little mixing between the two will be happening in the bottom region of the tool. So where you will have the little intermixing of the top as well as the bottom one. So but strength here is considered to be the function of the hook length which is there being formed. So typical hook geometry is of this kind. So here we can say the angle, or you can say the orientation of this hook as well as its length. So the hook can be very short or it can be a very big like this. So the hook height is measured and the hook angle or the orientation. These are the two parameters which are characterized to see their effect on the joint load carrying capacity. So hook height and the hook angle indicating the orientation of the hook. Okay, so there are two variants as such as far as the spot welding is concerned. In one of the variants, you know that when the joint is made in lap joint configuration between the two seats like this, okay, and this is the bottom one, right? So say when the hook is formed, this is the upper one. Say hook is formed, the joint nugget is the joint is formed, then a typical hole is left in one of the cases where in one of the variants of the frictionist spot welding, you just plunge the tool up to the desired depth in the bottom plate and then you take it out. So the plunging and withdrawing the tool, these are the two aspects. In that case, one typical hole is left in this type of the joints. So this hole or cavity is left in case of the frictionist spot weld joint. This is one type of the variant. In another case, this joint is the similar kind of the approach is similar to to develop the joint, but in that case this cavity which is being formed is refilled by the controlled deformation of the metal nearby. Controlled deformation of the metal which is in vicinity of the tool or wherever this cavity is being formed. So in one case you get in the frictionist spot welding, in one case you get the hole or the cavity wherever this kind of the joint is being made, and in another case the entire cavity is filled in. So this is the refilling kind of the thing that will be happening in development of the frictionist spot weld joint. So if you see the frictionist spot weld comes with the two variants where there is a cavity or hole is left at the joint location. So this hole can be the source of stress concentration or it can act as a stress reserve and thereby weakening the metal, weakening the joint. This is one thing. And the second one is where the refilling of the cavity is done so that it doesn't leave any kind of the hole. So no hole or the cavity is left in case of the frictionist spot weld joint which is developed. So the arrangement or the mechanism or the system for developing the refilled based frictionist spot weld, this is little complex and complicated and more advanced systems you need. While the frictionist spot weld with the hole can easily be developed using the simple vertical milling machine or any frictionist welding. So you need a very special tooling for developing the refilled type of the frictionist weld joint. In that case, you will see that there is a complete metallurgical continuity and there is nothing like a hook kind of formation, or even if it is there, it may be negligible here and there. So this is the frictionist spot weld of the type 1 where one cavity is left. So the rotating FSW tool is gradually plunged. Okay, and this plunging is done through the thickness of the top plate, and partially it is penetrated even in the bottom plate. Okay, and because of the frictional heat generation and thermal softening, metal will be flowing all around it. Okay, and this will be leading to the metallurgical continuity between the two components which are to be joined in lap joint configuration. And once this the plunging is over, stirring will be continued for a while, and then the tool is withdrawal. So the extraction or removal or withdrawal of the tool is done. So when you are withdrawing the tool, you will notice that this kind of the cavity will certainly be left in the joint where this kind of the friction stress spot weld is being made. And this is the actual photograph. You can see the kind of the joint cross section that is developed, and here you will see the kind of hooks which will be formed. Okay, which will be governing the joint strength. And this kind of the hook formation that you can see here in this the bottom this figure, what you can see, this is the tool, this is the upper plate, this is the lower plate. Okay, and this is the extent of penetration of the tool shoulder below the top surface, below the surface of the top plate. So this is necessary in order to have the consolidation or forging action needed for development of the joint. Okay, because metal will be flowing below the shoulder. Okay, and certainly little flow and the deformation will be happening here as well. So if you will notice here, there are the hooks are formed both the sides all along the, you see, circumference of the, because this is the front views, that's why you can see the two sides, but this kind of hook will be formed all along the periphery of the circular section weld. Okay, so the hook orientation, if you see the enlarged view of this, so say this is the typical hook geometry indicating the hook height. Okay, and the hook angle you can say, and this is the stir zone. So here the hooks are formed depending upon the tool geometry. Hooks are formed of the different orientations. Hook usually in the advancing side is much larger than the hook in the retreating side, because of the greater heat generation and the more plastic flow of the metal. And orientation can also be significantly different. It can be just vertical or it can be at certain angle. Okay, so basically the hook height and its angle, the hook angle, these are the two parameters which are used to characterize the hook geometry, which will be affecting. But certainly in the problem with this kind of the frictionless stress spot welding is that some kind of the cavity is left in the look at the location where the joint is being made. So this is one type of the one variant of the frictionless stress spot welding. Okay, the another variant is this. What we are doing in this case, you cannot see where is the top plate, where is the bottom plate, and the two have been completely mixed with each other. How it is happening for to see this? So it this kind of the this variant of the frictionless stress spot welding needs the specialized tooling. So you see this tool has three different components. One which will be used, which will be acting as a work holding or clamping device. It will be applying pressure. The second is the shoulder. Okay, and third one, so this is shoulder and this is pin. In the middle you have pin. Okay, right. This is clamp, as it is clear. So in any case, always whenever the certainly anvil or the base or good foundation is needed. So what is being done here in this configuration, what is being done, initially the clamps will come down and they will uh, uh, hold the workpiece very firmly like this. Okay, thereafter, you know, in one of the variants, your the shoulder comes down first, rotating shoulder, both will be rotating shoulder as well as pin. So rotating shoulder will also be developing the heat. Right, initially the pin is in the upper part, pin is moved up and shoulder is brought down. When the shoulder is brought down, so the metal will be softened and it will be flowing up like this. Okay, and thereafter, once if you find that sufficient the metal has flown, so you see in the stage 1 firm gripping and the rotation of the tool as well as the pin, so that some heat is generated. Then the pin is moved up and shoulder is moved down. Okay, pin is moved up and shoulder is moved down, so the softened metal will be flowing up. Okay, and then what we do, uh, the shoulder is moved up to the top level surface and the pin is moved down. So basically in this process of moving up and down of the shoulders and pin, we are trying to deform the thermally softened metals from both upper as well as the bottom plates partially, and deform them in such a way that the metallurgical continuity is realized. Okay, so the clamp, first what we are doing, this is one variant where first we are doing the clamping, then rotation of the shoulder and pin, developing the frictional heat and softening the metal in this region. Then pin is moved up and shoulder is moved down. Okay, so the metal is flown, will be flowing in the upside in the space where from the pin has moved up, and then the pin will be moved down. So this kind of the consolidation and forging action, or you can say simple upsetting, will be taking place. So initially there is a drawing and then there is a upsetting of the metal, and then entire assembly is moved up. Okay, so the joint of this kind of the geometry is formed. So in this case the weld is made where there is a continuous sturgeon formation, mostly in the upper plate and partially in the bottom plate. Okay, and the kind of the the macro section of this kind of the joint, if you see, this is obviously because of the frictional heat and deformational heat generation, there will be some heat affected zone, then there will be some TMAZ zone, and then stir zone. Okay, stir zone will be experiencing the similar kind of changes like dynamically recrystallized fine and equexed grain structure, etc. All those things will be there. But here you will have a simple joint formation without any kind of the hole, or under the optimum conditions it will be free from the discontinuities. Okay, so this is one of the variants of the friction stir spot welding. Another variant is almost the same, but there is a little difference which one is moving first and which one is moving down. This is that in this case the clamps are coming down first, and the shoulder and pin both are coming. Okay, and then the rotation will be softening the metal. All right, and in this case the pin is moved first, so whatever the deformed metal is there, that will be filled in the space due to the movement of the shoulder in upward direction. So shoulder is moved up and pin is moved down, and then shoulder will be also moved down while maintaining the level of the, while the pin will be moved up to the level of the top surface. So this is how the consolidation will be happening, and then entire assembly is moved up. So this is simple repetition or the similar kind of the arrangement, except the difference is which part is moved up and which part is moved down in a particular sequence. So initially what we did, we moved the shoulder down, and the pin was moving up, and then pin moved down. In this case our the pin is moving down, shoulder is moving up, and then the joint is formed subsequently in the third stage. Okay, so these are the three, you can say these two are the different variants of the refilled kind of the friction stir spot weld joint. Okay, and the one of the simplest one where a hole is left, that can easily be developed using the, so you need very good control for developing the refill kind of the frictionist spot weld joint. You need very good controls for the controlled movement of the shoulder as well as pin, in order to have the desired deformation of the seats to develop the metallurgical continuity. Okay, so this is what was about the friction stir spot welding. Okay, the lastly here it is about the friction surfacing. Friction surfacing is primarily used for modifying the surface properties. There are different ways of the surface modification. In one of the simplest thing is you just bring the metallurgical changes at the surface without any compositional change. So you can use work hardening, you can use phase transformation, etc. Okay. In the second method, you just make the certain kind of the chemical changes, bring carbon, nitrogen, vanadium, etc. at the surface. So you use the chemical composition modification. Third approach is you just develop the layer of the desired material at the surface so that the desired surface properties can be realized. Okay, so here this involves like addition of the metal or the material that you want to apply. Okay, so and that is why, since there is an addition of metal, so we call it as a allied joining process, which is done also in solid state. Like in arc welding, you can use SMAW, you can use a number of processes where there may be little melting or no melting, like in thermal spraying also. So those are like little high heat input processes, except there are multiple thermal spray processes which involve very limited heat input as well. But this is one of the variants which is based on the solid state joining for addition of the metal, just to modify the surface properties. Modify. So what we do basically is say, if you find your mild steel is not good corrosion resistant, then you can simply apply the austenitic steel of the desired material. If you find if you need very good kind of reflectivity, then over the mild steel you can apply aluminum, just like this. So as per the need, you can apply the desired material at the surface, so that you get the different set of the properties at the surface as compared to the bulk material. Okay, so based on this third approach of the surface modification, where addition of the metal is used, this is one of the approaches where without fusion the metal is deposited at the surface. This is one of the aspect. The second aspect related to the solid state joining for surface modification is what kind of the interface is being formed. So what is being done here, like the metal is used in form of pin. Pin is made of the metal to be deposited. Pin is made of the metal to be deposited, and then it is applied on the surface. So what we do basically, at the desired load, under the given a normal load, you apply the rotating pin on the surface of the metal, like the substrate over which the metal is to be deposited. So when the rotating pin made of the metal which is to be deposited is brought in contact with the substrate and it is rotated under pressure, it generates a lot of frictional heat, and because of this frictional heat you will notice that this metal is getting softened, and heat is generated to such a high extent that the softened metal starts getting deposited on the surface of the substrate. So idea behind here is, like, the metal to be deposited like this will be applied, like say this is the substrate, maybe mild steel, and low temperature metals like maybe copper alloy or brass, bronze, or any other metal. So you have to apply sufficient load and rotational speed so that enough high temperature is generated, and because of this high temperature you will notice that the base metal is sustaining. It is not a thing is happening, but the soft metal or the pin metal is getting deformed, or it is getting partially melted also, and then it is softened very badly. Okay, so whenever these things will be happening, you will notice it will start getting deformed, it will start bulging like this. Okay, so invariably you will see that the upsetting is taking place in the pin because of this heating, softening, and even partial melting. So once this starts happening, you will see the diameter at the bottom is much larger as compared to the pin diameter. So normal load coupled with the rise in temperature, thermal softening, all these will be causing the upsetting in the lower portion of the pin. And when you find that the sufficient heat generation has taken place, sufficient rise in temperature has taken place, there is partial melting has started, then metal will start getting sticking or getting deposited. So sticking and getting deposited, the metal, deposition of the metal with the substrate will start. Once this starts, you start moving the pin all along the line wherever the joint is, wherever the metal is to be deposited. So initially say pin is here, you will start moving it all along the line wherever it is to be deposited. So the metal is deposited like this. Then you cover the entire length, okay, one by one, in sequence, so that the entire surface is modified with the deposited metal. Okay, the surface layer will be comprising the metal which has been deposited with the help of this rotating pin. So here idea is not joining, or you see idea here is to add the metal at the surface for surface modification. And since it is using the friction basically, that's why it is called friction surfacing. So surfacing is nothing, it's just like adding something to modify the surface properties. And since here we are using the friction as a principal factor which is governing, or which is the principal cause for the deposition of the metal through the frictional heating, that's why it is called a frictional surfacing. Okay. It would be interesting to see really if the rise in temperature is high enough, then you may find there is a TMAZ zone, there is a HAZ zone in the base metal as well. So TMAZ, then HAZ, all those things can also be formed, and this can lead to the formation of, like say, Martensitic transformation or partial Martensitic transformation. All those things can be observed in the heat affected zone. So this is the simple principle of your the friction surfacing process. So what you have to do, you have to choose the suitable metal to be deposited, and accordingly you will be choosing the suitable rotational speed, translational speed, so that sufficient rise in temperature is realized at the interface to cause the thermal softening and deposition of the pin metal onto the surface of the substrate, so that the metal can be deposited. Idea here is to deposit the metal. So using the whiteboard I have explained what the friction surfacing is. So using this the slide, I am just trying to explain, like there is a requirement of the normal load or axial force. The pin is basically consumable, okay, because it will be deposited in this process of the surfacing, and this is the surface surface over which the metal is to be deposited. So it is termed as basically the base metal or the substrate. And since the frictional heat generated is significantly high to cause the thermal softening and even little partial melting at the bottom, so this will be causing the little upsetting of the pin material as well, and that's why you will get this kind of the morphology, and the metal will get deposited on the surface of the substrate like this, and you'll keep on moving the pin all along the direction wherever it is to be deposited. So these are, like say, already deposited the layers of the metal over the steel substrate, you can easily see, and this is the metal being deposited, and this is the kind of typical geometry or offset zone which is formed due to the thermal softening under the given normal load. And the rotating pin under the normal load, it will be moved all along the surface which is over which it is to be deposited. Okay, and this is just the schematic one. If you see the substrate and the modified zone, and if you cut it's a small section to see how does it look like, and then at the top surface it will be like there will be a thin layer of the metal which is being deposited, and further higher magnification if you see the layer of the metal which is deposited and the substrate. Okay, so now I'll show you one video. This is the pin material which has been heated. Of course the peak temperature is maximum at the surface, and then temperature will be decreasing. These are the different examples of the friction surfacing. Okay.